The title of my work is Effects of Residual Stresses on Interlaminar Radial Strength of Glass-Epoxy L-bend Composite Laminates, and the contributing authors are given below. Introduction. Curved laminates are a very common structural components in aircraft structure. These components are susceptible to failure by delamination across their thickness due to the lack of reinforcement, specifically in the curved region that acts as a stress tensor. As the curved laminates are processed at higher temperature and pressure, the residual stresses are developed primarily due to the differences in the coefficient of thermal expansion between the fibers and the matrices, and these stresses exist even after manufacturing. So these stresses may affect the structural integrity and the load bearing capability of the L-bend composite. So it is important to know the residual profile in these composites. The main aim of this work is to experimentally determine the residual stresses in the L-bend composites and to study the effects of these stresses on the bending strength of the L-bend composite. Manufacturing. The L-bend composites are manufactured by using two V-shaped mounts as shown in the figure and cured at room temperature. And the state of residual stresses in these composites is varied by post-curing these composites at higher temperature at 90, 135, and 180 degree Celsius. Then the residual stresses in each composite laminate is experimentally determined by using a commonly used method known as a slitting method. The residual stresses across the fiber and along the fibers are determined by slitting method. And the profiles of the relaxed strains and the residual stresses determined are shown in the figure. The composite laminates cured at higher temperature released more strains compared to the other composites. And the bending strength of the L-bend is determined by using a 4-point bending fixture as shown in the figure. And the load displacement plots for all the composite laminates are shown. The composites with 16 lamina has higher stiffness compared to the 12 lamina composites, and the interlaminar bending strength determined from this. The load for the initial delamination of the L-bend is given in the figure. As we can see, the thickness doesn't have any effect on the interlaminar radial stress. For example, the laminates cured at room temperature with 12 and 16 lamina almost have a same interlaminar radial stress, and the state of residual stresses also doesn't have any effect on the bending strength of the composites. So in order to understand the effects of the post-curing on the delamination resistance of the L-bend composites, the fractured surfaces of the 16 laminar composites is shown. As we can see, the laminates cured at the higher temperature show a better fiber matrix bonding, thus resulting in a higher delamination resistance, that is a higher bending strength. The conclusion that we can draw from this research are: the bending stress, the critical radial stress for delamination is appeared to be independent of the thickness of the laminates. Then the increase in the delamination resistance, that is the bending strength, is due to the improved fiber matrix bonding after curing at higher temperature, and the state of residual stresses doesn't have an influence on the interlaminar radial stress. Thank you.